Hello and welcome to Earth Science, Lecture 30, A Tour of the Solar System. Our ancestors long ago realized the motions of the planets through the sky, but it has been only a few hundred years since we learned that the Earth is also a planet that orbits the Sun. Even then, we knew little about the other planets until the advent of a large telescope. More recently, the dawn of space exploration has brought us far greater understanding of other worlds. We've lived in the solar system all along, but only now are we getting to know it. In this lecture, we'll explore our solar system like newcomers to the neighborhood. We'll begin by discussing what we hope to learn by studying the solar system, and in the process take a brief tour of the major features of the Sun and the planets. We'll also explore the major patterns that we observe within the solar system. So before we jump in, I just wanted to give an image here that is a little bit of perspective. So this is an actual image of Saturn, and you can tell that the Sun is behind Saturn in this image. What you'll also notice is a pretty white dot in between some of the rings of Saturn on the top left. So in my class I would ask, what do you think that object is? Some might say it's a moon of Saturn, but some probably get the hint that, at least where I'm taking this is actually an image of us. This is Earth. So I just wanted to throw this in maybe to give a little bit of perspective or scale when we're discussing our own solar system. So even in the scheme of our solar system, we're not so significant in a sense. But anyway, let us actually jump into the lecture. The Sun is the center of a revolving system, trillions of miles wide, consisting of 8 planets, their satellites, and numerous smaller bodies, such as dwarf planets, asteroids, comets, and meteoroids. An estimated 99.85% of the mass of our entire solar system is contained within the Sun. Collectively, the planets account for most of the remaining 0.15%. Starting from the Sun, the planets are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. You'll notice several clear patterns of motion among the large bodies of our solar system. For example, all planetary orbits are nearly circular and lie nearly in the same plane. So here you can see they almost look like complete circles, and in the bottom part of this image you can see a side view of our solar system. And note that they all lie almost exactly in the same plane, meaning none of them are really tilted away from the others too much. All planets also orbit the Sun in the same direction, that is counterclockwise as viewed from above the Earth's North Pole. Furthermore, most planets rotate in the same direction in which they orbit, with fairly small axis tilts. The Sun also rotates in this direction. And last, most of the solar system's large moons exhibit similar properties in their orbits around their planets, such as orbiting in their planet's equatorial plane in the same direction as the planet rotates. We consider these orderly patterns together as the first major feature of our solar system. Our theory of solar system formation explains these patterns as consequences of processes that occurred during the early stages of the birth of our solar system, which we will get to in our next lecture. Our brief planetary tour shows that there are 4 inner planets and 4 outer planets that are quite different from one another. We see that these two groups represent 2 distinct planetary classes, terrestrial and Jovian. Let's begin with terrestrial. The terrestrial planets, which I've highlighted with the red box, terrestrial meaning Earth-like, are the 4 planets of the inner solar system, that being Mercury, Venus, Earth, and Mars. These planets are relatively small and dense, with rocky surfaces and an abundance of metals in their cores. They have few moons, if any, and no rings. Their orbits are crowded in close to the Sun. We count our moon as a 5th terrestrial world, because its history has been shaped by the same processes that have shaped the terrestrial planets. The Jovian planets, where Jovian means Jupiter-like, are the 4 large planets of the outer solar system, that being Jupiter, Saturn, Uranus, and Neptune. The Jovian planets are much larger in size and lower in average density than the terrestrial planets, and they have rings and many moons. Their orbits are widely spaced at great distances from the Sun. They lack solid surfaces and are made mostly of hydrogen, helium, and hydrogen compounds. That is, compounds containing hydrogen such as water, H2O, ammonia, NH3, and methane, CH4. Because these substances are gases under earthly conditions, the Jovian planets are sometimes also called the gas giants. So when we compare these two different categories or classes of planets, we can kind of summarize everything into one small table like I have here. So the terrestrial planets are smaller in size and mass. They have a higher density because they're mostly made of rocks and metals. They have a solid surface. They have few, if any, moons with no rings and lie close to the Sun. The Jovian planets are essentially the opposite. So for my students, this is a good reference slide for you if you need to review the basic properties of these different categories of planets. So let's take a look at the terrestrial planets a little bit closer. All the terrestrial worlds have layered interiors. You're probably familiar with the idea of dividing the interior into 3 layers by density, as we've done in our geology portion of our class. So the Earth consists, or all these planets, consist of a core, a mantle, and a crust. The core is the highest density material region, consisting primarily of metals such as nickel and iron, which reside in the central core. Rocky material of moderate density, mostly minerals that contain silicon, oxygen, and other elements, form the thick mantle that surrounds the core, which you see in the red. And then the lowest density rock, such as granite and basalt, which are common volcanic rocks, form the thin crust, essentially representing the world's outer skin. The layered interiors of the terrestrial worlds tell us that they underwent differentiation at some time in the past, which, if you recall, means that all these worlds must have once been hot enough for the insides of their interior rock and metal to melt during their formation. The denser metals, like iron, sank to the center, while the less dense rocky material floated toward the surface. We can understand why the interiors are layered by thinking about what happens in a mixture of oil and water. Gravity pulls the denser water to the bottom, which drives the less dense oil to the top. This process is, again, called differentiation. So this figure shows these 3 layers for the 5 terrestrial worlds. Notice that Mercury has an unusually large core compared to the rest of its body. And the Moon has an unusually small core compared to the rest of its body. The reasons for both of these will be discussed soon. The 2 largest Jovian planets, Jupiter and Saturn, likely have small, solid cores consisting of iron compounds, quite like the cores of the terrestrial planets. And they also have rocky materials similar to Earth's mantle. Progressing outward, the layer above the core consists of liquid hydrogen that is under extremely high temperatures and pressures. Substantial evidence indicates that under these conditions, hydrogen behaves like a metal in that it allows electrons to move freely and efficiently conduct both heat and electricity. Jupiter's intense magnetic field is thought to be the result of electric currents that flow within a spinning layer of liquid metallic hydrogen. Saturn's magnetic field is much weaker than Jupiter's, due to its smaller shell of liquid metallic hydrogen. Above this metallic layer, scientists believe both Jupiter and Saturn are composed of molecular liquid hydrogen intermixed with helium. The outermost layer is a gaseous atmosphere, consisting mainly of a hydrogen and helium mixture, along with small amounts of water, ammonia, methane, and other substances. Uranus and Neptune also have small iron-rich, rocky cores, but their mantles are likely hot, dense water, methane, and ammonia. Like Jupiter and Saturn, they have atmospheres dominated by hydrogen and helium gases. The Jovian planets have very thick atmospheres composed mainly of hydrogen and helium, with lesser amounts of water, methane, ammonia, and other hydrogen compounds. By contrast, the terrestrial planets, including Earth, have relatively meager atmospheres that are typically dominated by carbon dioxide or nitrogen, and most small solar system bodies are airless. Two factors explain these significant differences: solar heating, in other words temperature, and gravity. These variables determine what planetary gases, if any, were captured by the planet during their formation of the solar system, and which were ultimately retained. During planetary formation, the inner regions of the developing solar system were too hot for ices and gases to condense. But the outer planets formed where temperatures were low, and so this allowed water vapor, ammonia, and methane to condense to form ices. As a result, the Jovian planets contain large amounts of these volatiles. As the planets grew, the largest Jovian planets, that being Jupiter and Saturn, also attracted large quantities of the lightest gases, hydrogen and helium, due to their strong gravitational fields. This explains why the Jovian planets have such thick atmospheres. How did Earth acquire water and other volatile gases? Well, it seems that early in the history of the solar system, gravitational tugs by the gas giants, mainly Jupiter and Saturn, sent planetesimals, in other words, small rocky bodies forming into planets, into very eccentric orbits. As a result, Earth was actually bombarded by icy objects, mainly comet-like objects, that brought in water and other elements. This was a fortuitous event for organisms that currently inhabit our planet. Mercury, our moon, and numerous other small bodies lack significant atmospheres, although they certainly would have been bombarded by icy bodies early in their development. Airless bodies develop where solar heating is strong or the gravities of those bodies are weak. Simply stated, small and warm bodies have a better chance of losing their atmospheres. Gas molecules are more energetic and hence faster moving on a warm body, and they need less speed to escape the weaker gravity of the smaller body. Mercury, the smallest and least massive of our 8 planets, has a low surface gravity, which makes holding onto an atmosphere challenging. In addition, because it is closest to the Sun, it is constantly bombarded by solar wind. Mercury, therefore, has the thinnest atmosphere of all the planets. The somewhat larger terrestrial planets, that being Earth, Venus, and Mars, retain some heavy gases, including nitrogen, carbon dioxide, oxygen, and even water vapor. However, their atmospheres are minuscule compared to their total mass. Early in their development, the terrestrial planets may have had thicker atmospheres. And over time, however, these primitive atmospheres gradually changed as light gases trickled away into space. For example, Earth's atmosphere continues to leak hydrogen and helium, that being the 2 lightest gases, into space. This phenomenon occurs near the top of the Earth's atmosphere, where the air is so tenuous that nothing stops the fastest moving particles from flying off into space. The speed required to escape a planet's gravity is called escape velocity. Because hydrogen is the lightest gas, it most easily reaches the speed necessary to overcome Earth's gravity. Billions of years in the future, the loss of hydrogen, which is one of the components of water, will eventually aid in drying out Earth's oceans, ending its hydrologic cycle. The massive Jovian planets have strong gravitational fields, which partially explains their thick atmospheres. Furthermore, because of their great distances from the Sun, solar heating is minimal. Because of the molecular motions of a gas is temperature dependent, even hydrogen and helium move too slowly to escape the gravitational pull of the Jovian planets. Cold temperatures also explain why Saturn's moon Titan, which is small compared to Earth but much farther from the Sun and therefore colder, retains an atmosphere. Size is the single most important factor in planetary cooling. Just as a hot potato remains hot inside much longer than a hot pea, a larger planet can stay hot inside for much longer than a small one. You can see why size is a critical factor by picturing a large planet as a smaller planet wrapped in extra layers of rock. The extra rock adds insulation, so it takes much longer for the interior heat to reach the surface. Size is therefore the primary factor in determining geological activity. The relatively small sizes of the Moon and Mercury probably allow their interiors to cool within 1 billion years or so after they formed. As they cooled, their lithospheres thickened and mantle convection was confined to deeper and deeper layers. Ultimately, the mantle convection probably stopped altogether. With insufficient internal heat to drive any further movement of rock, the Moon and Mercury are now quoted as being geologically dead, meaning that they have little to no heat-driven geological activity today. In contrast, the much larger size of Earth has allowed our planet to stay quite hot inside. Mantle convection keeps interior rock in motion, and that heat keeps the lithosphere thin, which is why geological activity can continually reshape the surface. Venus probably remains nearly as active as Earth, thanks to its very similar size. Mars, with a size in between those of the other terrestrial worlds, probably represents an intermediate case. It has cooled significantly during its history, but it probably still retains enough internal heat for at least some geological activity. So in general, the smaller the terrestrial world, the less internal heat it is likely to have retained. And thus, the less geological activity it will display on its surface. As a result, the less geologically active the world, the older and hence more heavily cratered its surface will be. This rule means that we can use the amount of cratering visible on a planet or satellite to estimate the age of its surface and how geologically active it is. So this is very important. We can actually date the ages of our planets to some extent simply using cratering. You can understand this idea by thinking about why the Moon has so many more impact craters than the Earth. Recall that all terrestrial worlds, regardless of their size or distance from the Sun, were battered by impacts during the heavy bombardment phase that occurred early in our solar system's history. Most impact craters were made during that time, and relatively few impact craters have occurred ever since. In places where we see numerous craters, such as on the Moon's surface, we must be looking at a surface that has stayed virtually unchanged for billions of years. In contrast, when we see very few craters as we do on Earth, we must be looking at a younger surface, one in which the scars of ancient impacts have been erased over time by other geological processes, such as volcanic eruptions or erosion. Interior heat plays another important role. It can help to create a global magnetic field. Earth's magnetic field determines the direction in which a compass needle points, but it also plays many other important roles. The magnetic field helps create a magnetosphere that surrounds our planet and diverts the path of high-energy charged particles coming in from the Sun. The magnetic field therefore protects Earth's atmosphere from being stripped away into space by these particles. Many scientists suspect that this protection has been crucial to the long-term habitability of Earth and hence our own existence. We can generalize these ideas to the other worlds. There are 3 basic requirements for a global magnetic field: an interior region of electrically conducting fluid, such as molten metal, convection in that layer of fluid, and at least moderately rapid rotation. Earth is the only terrestrial world that meets all 3 requirements, which is why it is the only terrestrial world that has a strong magnetic field. Mars's core is thought to be partially molten, but not hot enough to support convection, and as a result, it lacks a magnetic field. Venus does not have a magnetic field either, even though its core is thought to be molten and have a metallic layer much like Earth's. Presumably, its lack of magnetic field is either because the core is not hot enough to drive convection, or because the planet's 243-day rotation period is far too slow to generate a magnetic field. Researchers were surprised to discover that Mercury, despite its small size and slow 59-day period of rotation, does actually possess a measurable magnetic field, albeit only 1% the strength of Earth's. This may be the result of Mercury's partially molten metallic core, which is unusually large compared to the size of the rest of its planet. The same three requirements for magnetic fields also apply to the Jovian planets and stars. For example, Jupiter's strong magnetic field comes from its rapid rotation and its layer of convective metallic hydrogen that conducts electricity. The Sun's magnetic field is generated by the combination of convection of plasma and rotation. So we've looked at some of the general ideas of the planets. So let's just, before we jump into the details of our planets, let's just take a quick glance at each one. So what we're going to do is step from the Sun outward, just very quickly discussing a little bit about each part of our solar system. We will return in lecture 32 to each of the planets in more detail. So let's start at the middle of our solar system. We now know it's a heliocentric system where the Sun is the center. Let's start there. In terms of size and mass, the Sun is by far the largest and brightest object in our own solar system. It contains more than 99.8% of the solar system's entire mass, making it nearly 1,000 times as massive as anything else in the solar system combined. The Sun's surface looks solid in photographs, but is actually a rolling sea of hot hydrogen and helium gas at about 10,000 degrees Fahrenheit, or 5,800 degrees Kelvin. The surface is speckled with sunspots that appear dark in photographs, but only because they are slightly cooler than their surroundings. Solar storms sometimes send streamers of hot gas soaring far above the surface and even toward the Earth. The Sun is gaseous throughout, and the temperature and pressure both increase with depth. The source of the Sun's energy lies in its deep core, where the temperatures and pressures are so high that the Sun is a nuclear fusion power plant. Every single second, fusion is transforming 600 million tons of hydrogen into 596 million tons of helium. That missing 4 million tons is what becomes energy, according to Einstein's famous equation, E equals mc squared. Despite converting 4 million tons of mass into energy every single second, the Sun contains so much hydrogen that it has already shown steadily for almost 5 billion years and will continue to do so for another 5 billion years. The Sun is the most influential object in our solar system. Its gravity governs the orbits of the planets, its heat is the primary influence of the temperatures of planetary surfaces and atmospheres, it is the source of virtually all of the light in our solar system. Note that planets and moons shine by virtue of sunlight that they reflect. And in addition, charged particles flowing outward from the Sun, that is, the solar wind, help to shape planetary magnetic fields and influence planetary atmospheres. Nevertheless, we can understand almost all the present characteristics of the planets without knowing much more about the Sun than we have just discussed. To the first planet, or the closest one to the Sun, we arrive at Mercury. Mercury is the innermost planet of our solar system, and also the smallest of the 8 official planets. It is a desolate, cratered world with no active volcanoes, no wind, no rain, and no life. Because there is virtually no air to scatter sunlight or color the sky, you could see stars even in the daytime if you stood on Mercury with your back toward the Sun. You might expect Mercury to be very hot because of its closeness to the Sun, but in fact it is a world of both hot and cold extremes. Tidal forces from the Sun have forced Mercury into an unusual rotation pattern. Its 58.6-day rotation period means it rotates exactly 3 times for every 2 of its 87.9-day orbits of the Sun. This combination of rotation and orbit gives Mercury days and nights that last about 3 Earth months each. Daytime temperatures can reach a searing 797 degrees Fahrenheit, nearly as hot coals. At night, or in shadows, the temperature can fall below 238 degrees below zero in Fahrenheit, far colder than Antarctica in winter. Mercury's surface is heavily cratered, much like the surface of our moon. But it also shows evidence of past geological activity, such as plains created by ancient lava flows and tall, steep cliffs that run hundreds of kilometers in length. These cliffs may be wrinkles from an episode of planetary shrinking in its early history. Mercury's high density indicates that it has a very large iron core, perhaps because it once suffered a huge impact that blasted away its outer layers. Venus, the second planet from the Sun, is nearly identical in size to Earth. Before the era of spacecraft visits, Venus stood out largely for its strange rotation. It actually rotates on its axis very slowly and in the opposite direction of the other planets. So days and nights are very long, and the Sun actually rises in the west and sets in the east, instead of what we're used to here on Earth. Its surface is completely obscured from view by dense clouds, so we know very little about it until a few decades ago, when spacecraft began to map Venus with cloud-penetrating radar, discovering mountains, valleys, craters, and extensive evidence of past volcanic activity. We now know that an extreme greenhouse effect bakes Venus's surface to an incredible 880+ degrees Fahrenheit, trapping heat so effectively that nighttime offers no relief. Day and night, Venus is hotter than a pizza oven, and the thick atmosphere bears down on the surface with a pressure equivalent to that nearly a kilometer or 0.6 miles below the surface of our oceans on Earth. Far from being a beautiful sister planet to Earth, Venus resembles a traditional view of hell. The fact that Venus and Earth are so similar in size and composition, but so different in surface conditions, suggests that Venus teaches us an important lesson, which we've discussed previously in our climate change lecture. In particular, if you didn't see that lecture, Venus's greenhouse effect is caused by carbon dioxide, the same gas that is primarily responsible for today's global warming on Earth. Perhaps further study of Venus may help us better understand and solve some of the problems that we face here at home. Speaking of home, beyond Venus, we next encounter our home planet, Earth, the only known oasis of life in our solar system. Earth is also the only planet in our solar system with oxygen to breathe, ozone to shield us from deadly solar radiation, and abundance of surface water to nurture life. Temperatures are pleasant because Earth's atmosphere contains just enough carbon dioxide and water vapor to maintain a moderate greenhouse effect. Despite Earth's small size, its beauty is striking. Blue oceans cover nearly 3/4 of the surface, broken by the continental landmasses and scattered islands. The polar ice caps are white with snow and ice, and white clouds are scattered above the surface. At night, the glow of artificial light reveals the presence of an intelligent civilization. Earth is the first planet in our tour with a moon. The moon is surprisingly large compared with Earth, although it is not the largest moon in the solar system. Almost all other moons are much smaller relative to the planets that they orbit. The leading hypothesis holds that the moon formed as a result of a giant impact in Earth's early history. The next planet on our tour is Mars, the last of the 4 inner planets of our solar system. Mars is larger than Mercury and the Moon, but only about half Earth's size and diameter. Its mass is about 10% that of Earth. Mars has 2 tiny moons, Phobos and Deimos, which probably were once asteroids that were captured into the Martian orbit early in its history. Mars is a world of wonders, with ancient volcanoes that dwarf the largest mountains on Earth, a great canyon that runs nearly 1/5 the way around the planet, and polar caps made of frozen carbon dioxide or dry ice and water. Although Mars is frozen today, the presence of dried-up riverbeds, rock-strewn floodplains, and minerals that form only in water offers a clear piece of evidence that Mars had at least some warmer and wetter periods in its past. Major flows of liquid water probably ceased at least 3 billion years ago, but some liquid water persists underground, perhaps flowing to the surface on occasion. Mars's surface looks almost Earth-like, but you wouldn't want to visit without a spacesuit. The air pressure is far less than that on top of Mount Everest. The temperature is usually well below freezing. The trace amounts of oxygen would not be nearly enough to breathe, and the lack of atmospheric ozone would leave you exposed to deadly ultraviolet radiation from the sun. Happy thoughts. To reach the orbit of Jupiter from Mars, we must traverse a distance that is more than double the total distance from the Sun to Mars, passing through the asteroid belt on the way. Upon our arrival, we find a planet much larger than any we have seen so far. Jupiter is so different from the planets of the inner solar system that we must adopt an entirely new mental image in terms of a planet. Its mass is more than 300 times that of Earth, and its volume is more than 1,000 times that of Earth. Its most famous feature, a long-lived cyclonic storm called the Great Red Spot, is itself large enough to swallow 2 or 3 Earths. Like the Sun, Jupiter is made mostly of hydrogen and helium and has no solid surface. If we plunge deep into Jupiter, the increasing gas pressure would crush us long before we ever reached its core. Jupiter reigns over dozens of moons and a thin set of rings that are too faint to be seen in most photographs. Most of the moons are very small, but 4 are large enough that we'd call them planets or dwarf planets if they orbited the Sun on their own. These 4 moons, Io, Europa, Ganymede, and Callisto, are often called Galilean moons because Galileo is who discovered them, and they display varied but interesting geology. For example, Io is the most volcanically active world in the solar system. Europa has an icy crust that may hide a subsurface ocean of liquid water, making it a promising place to search for life. And Ganymede and Callisto may also have subsurface oceans, and their surfaces have many features that remain mysterious. The journey from Jupiter to Saturn is a long one. Saturn orbits nearly twice as far from the Sun as Jupiter. Saturn, the second largest planet in our solar system, is only slightly smaller than Jupiter in diameter. Its lower density makes it considerably less massive, about 1/3 that of Jupiter. And like Jupiter, Saturn is made mostly of hydrogen and helium with no solid surface. Saturn is famous for its spectacular rings. Although all 4 of the giant planets have rings, only Saturn's can be easily seen. The rings look solid from a distance, but in reality they are made of countless small particles, each with orbits around Saturn like a tiny moon. These particles of rocks and ice range in size from dust grains to city blocks. We are rapidly learning more about Saturn and its rings through observations made by the Cassini spacecraft, which has orbited the planet since 2004, but at least between the time of this book being written that I'm using and my discussion, Cassini has been lost into the atmosphere, if I recall. Cassini has also taught us more about Saturn's moons, and has revealed that at least 2 moons are geologically active today. Enceladus, which has ice fountains spraying out from its southern hemisphere, and Titan, the only moon in the solar system with a thick atmosphere. Saturn and its moons are so far from the Sun that Titan's surface temperature is a frigid negative 292 degrees Fahrenheit, making it far too cold for liquid water to exist. However, studies by Cassini and its Huygens probe, which landed on Titan in 2005, have revealed a remarkably Earth-like landscape, including an erosion-carved surface with riverbeds and lakes, except that these features are shaped by extremely cold liquid methane or ethane rather than liquid water. It's another long journey to the next stop on our tour, as Uranus lies twice as far from the Sun as Saturn. Uranus is much smaller than either Jupiter or Saturn, but is still much larger than Earth. It is made largely of hydrogen, helium, and hydrogen compounds, such as water, which is H2O, ammonia, which is NH3, and methane, which is CH4. Methane is what gives Uranus its pale bluish-green color. Like the other giants of the outer solar system, Uranus lacks a solid surface. More than 24 moons orbit Uranus, along with a set of rings somewhat similar to those of Saturn, but much darker and more difficult to see. The entire Uranus system, that is its planets, rings, and moons, is tipped on its side compared to the rest of the planets. This extreme axis tilt may be the result of a cataclysmic collision that Uranus suffered as it was forming, and it gives Uranus the most extreme seasonal variations of any planet in our solar system. If you lived on a platform floating in Uranus's atmosphere near the North Pole, you'd have continuous daylight for half of each orbit, or 42 years. Then, after a very gradual sunset, you'd enter into a 40-year-long night. The journey from the orbit of Uranus to the orbit of Neptune is the longest yet in our tour, calling attention to the vast emptiness of our outer solar system. Nevertheless, Neptune looks nearly like a twin of Uranus, although it is more strikingly blue. It is slightly smaller than Uranus in size, but a higher density makes it slightly more massive, even though the two planets share very similar compositions. Like Uranus, Neptune has been visited only by the Voyager 2 spacecraft. Neptune has rings and numerous moons. Its largest moon, Triton, is larger than Pluto and is one of the most fascinating moons in the solar system. Triton's icy surface has features that appear to be somewhat like geysers, although they spew nitrogen gas rather than water into the sky. Even more surprisingly, Triton is the only large moon in the solar system that orbits its planet backwards, that is, in a direction opposite to the direction in which Neptune rotates. This backward orbit makes it a near certainty that Triton once orbited the Sun independently before somehow being captured into orbit around Neptune. Well, we conclude our tour at Pluto, which reigned for some 75 years as the 9th planet of our solar system. However, the 2005 discovery of the slightly larger ERIS and the fact that dozens of other recently discovered objects are not much smaller than Pluto and ERIS, this led scientists to reconsider the definition of a planet. The result was that we now consider Pluto and ERIS to be dwarf planets. That is, they're too small to qualify as official planets, but large enough to be round in shape. Several other solar system objects also qualify as dwarf planets, including the largest asteroid of the asteroid belt named Ceres. Pluto and ERIS belong to a collection of thousands of icy objects that orbit the Sun beyond Neptune, making up what we call the Kuiper Belt. The Kuiper Belt is much like the asteroid belt, except it is farther away from the Sun and composed more of comet-like objects rather than rocky asteroids. Pluto's characteristics help us to think about what it would be like if we visit this distant realm. Pluto's average distance from the Sun lies far behind Neptune, as Neptune lies beyond Uranus, making Pluto extremely cold and quite dark even in daytime. From Pluto, the Sun would be little more than a bright light among the stars. Pluto's largest moon, Charon, is locked together with it in synchronous rotation, so Charon would dominate the sky on one side of Pluto, but never be seen from the other side. And so I leave you with this table. There's a lot to look at here, but again, this is one of those reference slides. So if you're in my course and you have the textbook, you'll see this in your textbook, but I figured I'd add this in just as a good reference for students that perhaps do not have their book. So this shows basically any property you would need for this class for all of the different planets. To be clear, you do not need to memorize all this if you're in my class. In fact, you don't really have to memorize any of it. Just get a general idea of how everything trends. So let's conclude this lecture with two short questions. Number 1, which of the following is a Jovian planet? Okay, so remember, Jovian planets are the large gaseous planets of the outer solar system. The only one that fits out of these 4 is Saturn, because the Jovian worlds are Jupiter, Saturn, Uranus, and Neptune. Question 2. The terrestrial planets have blank atmospheres than the Jovian planets, due to solar heating and blank. So you have 2 answers here, separated by commas. Well, the terrestrial planets, that being the Earth-like planets, we definitely have smaller atmospheres than the Jovian worlds. They're literally called the gas giants. And it's due to solar heating as well as gravity. Those worlds are bigger and more massive, so their gravity is stronger, and so they hold on to more gas. All right, so with that, we're going to hop over to lecture 31, where we learn about the formation of this solar system, and then 32 will be a look at the planets in more detail. So as always, thanks for watching, and have a great day.